Let's continue with this example here. Again, it's a system of two equations with two variables, and let's try the approach we used in the previous sections, where we take this set of equations and write it out as a multiplication of a matrix A, a vector xy, which we will denote with x, and it is equal to some vector b, in our case 2, 4. Now if you look at these equations, there's already something fishy about these equations, so see if you can spot it. I'll let you know in a second. But if we take this and we have our equation a times x is equal to b, well, we want to use the approach where we take the inverse. Times a times x is a inverse b, and we know that a times a inverse is equal to the identity matrix times x is a inverse b, and so x is equal to a inverse b. Now if we can take this approach and we can calculate A inverse, it's an easy way to find the solution. But let's look at the matrix A. And first let's look at the determinant of A, which is equal to 1 times 4 minus 2 times 2 is equal to 0. So A has no inverse. This doesn't mean that there aren't any solutions, because let's look at the combination x is equal to 0 and y is equal to 1. Well, if x is equal to 0 and y is equal to 1, we get 0 plus 2 equals 2, and we get 0 plus 4 equals 4. So this is a solution. Let's look at x is equal to 2 and y is equal to 0. Let's see, okay. 2 plus 0 is equal to 2, and 2 times 2 is 4, plus 4 times 0 is 4. This is also a solution, and x is 4, and y is equal to minus 1. And if we check this, this is also a solution, and the list goes on and on and on. There are, in fact, infinitely many solutions to this set of equations. So something strange is happening. The first important thing is that if we try to use this approach, it fails because A has no inverse. That doesn't mean there are solutions, as we have proven here, is that there are, in this case, infinitely many solutions. This approach, there's my green marker, well, red marker. This approach does not work in this case because A has no inverse. We'll have to find a different strategy. But let's look at what has happened here. So there's something going on, and perhaps some of you have already spotted it. The second equation is simply the first equation multiplied by 2. If we want to have a single solution for a set of two equations, these equations need to be what's called independent. One cannot simply be a multiple of the other. And if we have 3 equations, you can't have the third be some kind of combination of the first 2. They all have to be independent. And how can we visualize this? Well, for a system of 2 equations with 2 variables, this is something we can visualize, because each equation represents a line in the xy plane. So we have 4 situations where, well, the first example and the second example were 2 lines that intersect in a single point. The solution here is a single point, and this is the case for which this method does work. But we can have so this is situation 1. Situation 2 is that these lines fall exactly over each other. So we have one line, and the second line is the same as the first line, and that's the case in this situation, because here we have the line y is 1 minus x over 2, and here's the line is exactly the same. Y is 1 minus x over 2. just rewrite these and isolate y. Now, if we have two lines that are completely the same, we get infinitely many solutions, because every point on this line is a solution to this set of equations. Now, the third situation is where the lines don't cross. There is no intersection between these lines, so there are no solutions. And this is the case for any 2x2 system, is that depending on basically how these two lines behave, if they're in this configuration, this one or this one, there can be a single solution, there can be infinitely many solutions, or there can be no solution at all. And this is the case for all systems of linear equations. Doesn't matter how big or how many variables, how many equations, there is always the situation where you have one single solution, no solutions, or infinitely many solutions. And infinitely many, as we will see in 3x3 examples, can take on different forms. But if we have a 2x2 set, so two equations, two variables, there's the two lines will intersect, will run parallel, or are identical, and these are the three options we have. And in the next part, I will show you how this works for a 3x3 system.